Hi viewers, welcome back to another video. In this particular video, I'm trying to drive home the concept of vibration isolation and some terms that we often hear of, that is force transmissibility and displacement transmissibility. Okay, so let's get started. So this, before we dive into the maths and all those things, let's think about few applications, real life applications where we really come across displacement transmissibility and force transmissibility. This is one example. Here you have a jet engine connected to the wings of an aircraft. In this particular scenario, as the jet engine operates, it generates a lot of vibration, and ideally we need a system which will transfer less amount of this engine vibration to the wing and thereon to the passengers, because we don't need our passengers to feel or to experience all this vibration which is coming here in the engine. Make sense? In fact, the same condition applies if you're riding a bicycle on a wavy road. So this is the shock absorber. This is a mechanical model. Here you have your wheel and this is your wavy road. The disturbances in the road should not cause much of a trouble to the passengers. That in effect, that means whatever disturbances that this particular portion will feel due to the wavy road, it should not be transmitted upwards, or it should not be transmitted to the passenger. Let's go and discuss about the third example as well. In this model, we have a building as shown here. Now this building is modeled against earthquakes like this. Earthquakes are basically in which your back base is moving. So I'm modeling the earthquake vibration like this. I'm subjecting this particular portion, the base, to a non-displacement y of t. Then I am interested in x of t, how my building will respond to that kind of a base excitation. So these are a few examples where we talk about force transmissibility, or where we talk about displacement transmissibility, and these are the scenarios where we have to design our structure for vibration isolation. We just now saw few real life examples. Now let's formulate everything what we have talked about in a mathematical form. So we have a equivalent mechanical model here. This is the base and this is the mass we are talking about. For example, this will be your road. Your road is having a wavy pattern, and this will be the cabin where your passengers are sitting. In an engine case, in a jet engine case, this will be the jet engine which is producing or which is vibrating at a given amplitude and a given frequency, and this could be your cockpit where your people are sitting. So depending upon that, we are depending upon each of the applications, this base can be thought of something, or the little m can be thought of as something else. So I'm assuming that my base is moving harmonically with an amplitude of capital A and with a frequency of omega, and I'm assuming that this particular mechanical system which is sitting on top of the base is having a natural frequency of omega n. Having said all these things, so now this is the excitation for this particular system. Now the response can be written like this. Since the excitation is having a frequency of little omega, my response will also have a frequency of omega. And always remember that this particular capital X of I omega is a complex number, so it will have a magnitude as well as a phase. I won't get into the mathematical details, but this is the mathematical expression for the amplitude of the response. This tells you briefly, when your base is vibrating with an amplitude of capital A, then your system will have an amplitude of this much, where zeta is the damping ratio, C is the viscous damping coefficient, and Cc is the critical viscous damping coefficient, and R is the ratio of frequencies, where omega is the frequency at which my base is vibrating, and omega n is the natural frequency of my system that I am interested in. Make sense? If you observe this particular equation very keenly, you can see that actually if I take the ratio x of I omega by A, then that tells you whether the excitation is getting magnified or is it getting reduced. So with that kind of a logic, we define displacement transmissibility like this. Always remember that my base is vibrating with an amplitude of A, capital A, then this is the amplitude with which this particular mass, little m, will be vibrating. So that's why that is called displacement transmissibility. For the sake of explanation, let's take an example. Let's say in that jet engine example, my jet engine is having an vibration with an amplitude of, for example, let's say 10 mm. So your jet engine is vibrating with an amplitude of 10 mm, and let's say my displacement transmissibility is 5. Then it's a pretty bad situation, because your jet engine is vibrating with a displacement or an amplitude of 10 mm, then this particular portion where your passengers are sitting, it will see a displacement or an amplitude of 50 mm. That portion will also vibrate, but with a much larger amplitude. So for designs like this, design of the cockpit, you need to have a displacement transmissibility value which is very small, let's say in the order of 0.1 or maybe even less than that, so that you see a particular amount of vibration in your jet engine that won't get transferred to the region of your interest. Let's say for the same example, if you have a 10 mm vibration in the jet engine, then you will see just 1 mm in your cockpit, like that. It's just an example. Don't take them seriously, don't take those numbers seriously, because I've never designed anything of that sort in all my career. Okay, now having understood what is displacement transmissibility, let's get into the nuts and bolts of force transmissibility. So let me give you a theoretical explanation of force transmissibility first, before diving into the maths. So this is the mathematical model that we were talking about, and in this you can see both the force spring and the damper will see a relative displacement of x minus y. And when we take the free body diagram of this particular mass, this particular mass represents the bicycle, and for a bicycle example, this represents the person, how much force he is feeling. If you take the free body diagram of this particular portion alone, then we can see that there are two forces acting on this thing, which is k into x minus y coming from the spring, and there is a c into x dot minus y dot which is coming from the damper. This is the net force which will be transmitted from the base to the particular region of interest. So I won't get into the details of maths. We arrive at an expression for this force transmissibility like this. I'm not explaining it. I will just scroll through these equations, pause or scroll down at your own pace, understand what each of these equations are doing at your free time. This is very simple. I am not explaining. Then you can arrive expressions like this. I'm taking the amplitude of the transmitted force over here. Then what I'm trying to tell you is that I'm trying to non-dimensionalize this whole thing. I'm telling you, let's say I'm not oscillating my base. My base is no more vibrating. I'm just pushing my base upward by an amount, let's say capital A. Initially it was vibrating with an amplitude of capital A. Now I'm just pushing it. It's not a vibration. It's just like I'm pushing this particular base up in the upward direction by a fixed amount like A. Then the force felt by this particular mass over here will be K times A. Now this is used for non-dimensionalizing the whole thing. Now you can see, after doing all cranking this mathematical wheel, we are arriving somewhere here. So this particular quantity over here tells you what is the force transmitted to the region of interest, or what is the force felt by the little m when there is no vibration, when we are just moving the base by a fixed amount or by the same amount that of the amplitude capital A. Then this is the force transmitted to the region of interest, or to the cockpit. That may be the cockpit, that may be the passenger in a bicycle, and it goes like this. And it can be the building also when we are modeling earthquakes. So that's it. This is force transmissibility. This is the expression for force transmissibility, and this is the expression for displacement transmissibility. They are not the same. There is a little r whole square term in the force transmissibility. Just keep in mind. The next thing I want to show you is that how these things vary with respect to little r, which is the frequency ratio. So I told you the whole aim of this exercise is vibration isolation. I need to design structures such that this particular vibration of the base won't get transferred to the structure of interest or to the region of interest. And in the next few minutes, let's see how we can do that. For that, we need to plot both these quantities with respect to little r and see at which regions we are able to minimize this whole fraction. So this is how the displacement transmissibility will look like. A few things to be noted. If you look at this curve carefully, when your r value is very small, the curve starts from value equal of a value of displacement transmissibility equal to 1. That means it makes sense, because when your frequency is 0, you're just moving the base by a certain amount, your mass will also see the same amount, your little m will also see the same amount of displacement. So that makes sense. Displacement transmissibility at that point is simply 1. The other key observation is that for a value of omega by omega n equal to root 2, you can see, irrespective of the amount of damping present in the system, all the time my displacement transmissibility is equal to 1. It's a good point to be noted. So if I want to design a system where I need vibration isolation, I better keep my system in this regime. That means I should design, or I should decide upon the value of omega n so that your whole system works somewhere around here, where your displacement transmissibility is less than 1. So if your base is vibrating with an amplitude of 10 mm, then your structure won't see that 10 mm. It may see 0.1, it may see 0.01 according to the value of displacement transmissibility. Moreover, as you increase the amount of damping in the system, you can see here in this particular regime, for values omega by omega n less than root 2, you can see damping helps, because as you keep increase the amount of damping present in the system, then you can see the amplitudes are coming down. The values for the displacement transmissibility is coming down, so it helps. But it is quite counterintuitive in the next regime, where values of omega by omega n is greater than root 2. Here you can see as amount of damping increases, the value for displacement transmissibility goes up. So this should be remembered, because this is simply counterintuitive, because you tend to think like when I'm introducing damping into the system, I expect my displacement transmissibility to go down, but that is not the case all the time. So just keep this in mind. So I think if you need to design your vibration isolation, the parameters that you need to play around is the zeta value and your omega n value. So you should play around these two values, which are at your disposal, at the disposal of a particular designer, so that you can keep your passengers safe and you can give them all the comfort. I hope so. That's a key takeaway from this whole thing. You need to be having a good grip of this curve and this concepts what you are just seeing, what you are just shown. So that's it. Thanks for watching.